Good evening, everyone, and welcome to ScienceFest. This evening, we will be presenting space veggies using quantum dots to help grow vegetables on Earth and in space. We're delighted to have this evening Dr. Matt Bergren. Dr. Bergren is UbiQD's Chief of Product. He received his Bachelor's of Science in Engineering Physics at Colorado School of Mines and received his PhD in Applied Physics from the Colorado School of Mines in 2014 while performing research at the National Renewable Energy Laboratory, NREL, in Golden, Colorado. Before joining UbiQD in the fall of 2015, Dr. Bergren held a postdoc position at the National Renewable Energy Laboratory. It's an honor to welcome you this evening, and Matt, please go ahead and take it away.
Thank you so much, Ren, and thanks for everyone who's joining this evening right before dinner. Hopefully this will get your appetite going a little bit on some of the work we're doing here at UbiQD, focusing in on vegetable growth with our nanotechnology.
Matt, I'm sorry, let me just interrupt real quick. I forgot to mention that Matt will be talking and then answering a few questions afterwards. So please go ahead and enter your questions into the Q&A there down at the bottom of your screen, not on the chat, in the Q&A. I do also just want to mention that we will be recording this and it will be available later under the event schedule section. And then lastly, I do just want to say thank you to UbiQD for being a ScienceFest sponsor this year. And please visit their virtual booth Saturday at Discovery Day. Now, Matt, go ahead and take it away.
Awesome. Thank you so much, Ren. Yeah, we're happy to be a part of this every year. It's a great event, and I'm really happy to be giving the talk this evening. So I just wanted to start off introducing myself a little bit and giving you my background. As Ren mentioned, my name is Matt Bergren. I'm the Chief of Product at UbiQD here in Los Alamos. My background, I have a technical background. I have a PhD in Applied Physics from Colorado School of Mines. Did a couple postdocs, a short one at the National Renewable Energy Lab, focusing in on photovoltaic energy and looking at nanomaterials there. And then I actually traveled overseas to South Korea and did a postdoc at Sungkyunkwan University, which is about an hour south of Seoul in South Korea, looking at a different type of nanotechnology, which were 2D semiconductors, again, for solar energy harvesting. I joined UbiQD in 2015 as their first hire outside of the founder, Hunter McDaniel, who spun the company out of Los Alamos National Laboratory. And we've been growing ever since. So let me give you a little bit of a rundown about the company here. So we were established in 2014. As I mentioned, we're a spinoff from LANL. We're licensing technology from the National Laboratory, as well as MIT and the University of Washington and Western Washington. The IP that we're licensing from these different institutes encompass a lot of different things, from the composition of our material to the way that we manufacture it, to some applications that are covered as well. So what is UbiQD? UbiQD stands for Ubiquitous Quantum Dots, which I'll be telling you a little bit more about here in a few slides. But at the heart of the company, we're an advanced materials company powering product innovations in a few different industries, mainly in agriculture, energy, and security. And so, you know, I have a few different pictures here showing these different technologies. I'll be focusing on agriculture today, but be happy to talk to you guys about some of our other segments as well, if you're curious. Wanted to highlight our team. We have a really excellent team of 14 full-time employees. We like to say they're rock stars. And so what do you do with rock stars? You take them out rock climbing when you want to go out as a company. So this is a picture of us last year up in the Jemez Mountains behind us, up at Las Conchas, doing some rock climbing. Like I mentioned, we are located in town. We're on the edge of town as you're coming up the hill, or just there on your right. Picture of our headquarters there in the bottom right. And we're excited to be here and be close to the proximity and have that relationship with the scientists as well as the technology coming out of that. So it's one of the things we're proud of, and are continuing to want to stay here for the long term. Before I get into some of the technical part of the talk, I did want to cover some of the basis of the science that's going to be used throughout our technology and the materials that we are manufacturing at UbiQD. And we're going to talk a lot today about color and light and how that can affect different things, specifically plants. And so to do that, we need to talk about color. And so I wanted to put up this electromagnetic radiation plot. So it kind of gives you this, the range of different radiation levels, you know, depending on how energetic they are, what kind of wavelengths they have. You know, we talk about radiation typically in as a wave or as a particle. In this case, you know, we're talking about it in waves. So we have a wavelength. The longer the wavelength, the redder the color or less energy the radiation might be. So that's goes all the way out to things like radio waves, where, you know, they're not interacting with our body, is a good way to think about how much energy they have. Or as we go to the left side of that table, we see things like gamma rays or X-rays or ultraviolet light, which we know can damage our bodies or have health consequences. So that's how you can keep track of, you know, what radiation might be higher energy or lower energy, which will be important for our applications. And then there's this small section right down in the middle there about that shows the visible spectrum. And this is what we interact with every day. It's how we see things. It has a full color spectrum of the rainbow, spanning from about 400 nanometers wavelength out to 700 nanometers wavelength. And so, you know, you have our bluer colors at higher energy on the left and redder colors at lower energy on the right. So that's kind of your crash course on electromagnetic radiation, and specifically light, visible light and color. So next I wanted to go into a property of our materials that is key to all the applications that we're using them for. And that's photoluminescence, which is a scientific term for saying light conversion. Basically, photoluminescence is a property of a material that if it absorbs energy, usually in this case in the form of light, it can excite an electron in that semiconductor, for example. And so I have this kind of quick cartoon diagram of what's going on here. I have my arrow showing energy being applied to the system. I have two different levels. We call them the relaxed state or an excited state, just in general. And there's a gap between those. And typically we call that a band gap or an energy gap between those two states. And so when that light comes into the material and is absorbed by the material, essentially you can get electrons that are typically residing in the relaxed state to be excited, and they bump up to that next level or in an excited state form. But they don't want to stay there for very long, and they will want to relax back down to the ground state. And one of the ways they can do that is by emitting a photon of light or a different color of light. And that color of light that's emitted is completely dependent on that energy gap. And so you can imagine if the material itself has a gap that's larger, that means there's more energy that's going to be coming off from that light, and you're going to have a bluer color. So for example, in my pictures here on the bottom, the green material there is being illuminated by ultraviolet light, and it's glowing green because its gap is larger than, say, the material here on the right, which is glowing a red color. In that case, the energy gap is actually smaller, so it'll emit a longer wavelength light or a smaller energy. And then obviously the orange in between is somewhere in between those two levels. So keep that in mind as I talk about our materials and how we get to different colors. So, you know, our core competency at UbiQD, and it's in our name, is a nanotechnology called quantum dots. Quantum dots are very unique in the sense that they have this photoluminescent property, but we can tune it. And what I mean by that is by changing the size of these quantum dots or nanocrystals, we can actually change that gap that I mentioned in the last slide. So by essentially growing them to larger sizes or keeping them at a smaller size, we can tune what color of light they might emit after absorbing UV light or blue light, for example. This material is very efficient at doing this, and that's one thing that our team has worked very hard at, is to make sure that all of the colors that the material can emit are very efficient. We're always striving for 100% conversion efficiency. So light absorbed versus light that's emitted. We want that to be a 1-for-1 type of ratio. And so, you know, this is our core technology. We're really focused in on applications that can change the color of light and using these quantum dots to do so. I did want to take a quick second and talk about nanometers and nanotechnology, because sometimes when we talk about really small things, like on the scale of nanometers, we don't really relate to what that feels like. And so to give you something to gauge that against, I have a electron microscope image of something that's small that we all know and interact with, and that's human hair. And so typical human hair is around 100 microns in diameter. And to give you an idea of how small the quantum dots compared to that width of a human hair, they're 20,000 times smaller. So vanishingly small. You can only see them with these types of electron microscopes. And so when you're at that size range, that's really where the magic happens, and why quantum is in the name is quantum physics come into play when you're in that size regime. And that's how we're able to do this tuning of that band gap. So at UbiQD, you can imagine quantum dots. There's a lot of different types of compositions out there today that you may have read about in research or even in commercial settings. What sets us apart is our composition, specifically this copper and zinc-based material, copper indium disulfide with a zinc sulfide shell. And what our value proposition is with this material is, first and foremost, we don't suffer from the toxicity issues that other mature quantum dot materials that are out on the market suffer from. So what I mean by that, there's no heavy metals like cadmium or lead, or they're not a known carcinogen like indium phosphide, things of that nature. And so that really allows us to be able to go after applications that use a lot of quantum dots. We don't have to, you know, really seal them up and use only a sparing amount like you might with TVs, for example. And so it's going to let us tackle some of these bigger problems and bigger challenges that may have a bigger impact on the Earth. So that's exciting. The second value proposition we have with our materials is the way that we make it. So we have a different process than most quantum dots on how we synthesize the material. And to put it pretty simply, my chemists would roll their eyes if they heard me say it this way, but it's as simple as putting precursors together into a reactor, heating them up to a temperature, and letting that reaction take place for a certain amount of time. The longer the reaction goes, you can think the bigger the crystals, the quantum dots will grow, and that will change that luminescence, the color that they're glowing. So that's different than some other complicated, more complicated manufacturing methods for quantum dots. And that's going to allow us to be able to scale as we need to meet demand. And then finally, we have an inherent stability with our materials, which is good for, you know, going into things like greenhouses where that might be high humidity or high light or high temperature. Our materials can survive very well in kind of harsh conditions. So that really allows us to tackle some of these applications that we're working on. Speaking of applications, I just kind of wanted to give a brief overview of where quantum dots might be out on the market today, and kind of where UbiQD is situated in this area, at least where our main focuses are. And so with quantum dots, the main place that you'll see them today outside of what we're doing is in displays. Many of you probably own TVs that have QLED displays or talk about quantum dots. And the main value proposition there is that you can make very pure colors with the quantum dots these manufacturers are using. So you can get very pure reds and greens, which mixed with a nice pure blue LED, you can get very realistic colors, which is great for viewing. There's also lighting, which quantum dots are being considered for. There's products out there, they're not widespread, but same idea, we can create a custom spectrum with LED lights is the idea. So maybe you want to mimic sunlight, so you have a good color rendering index. You can see colors very clearly without any bias to them. Potentially in retail areas, you might want to make them be more red or more blue, depending on maybe what you're selling or what colors you want to show up. and things of that nature. So that's another application that quantum dots can be used for. The three that we are working in are in anti-counterfeit security inks. So making a optical signature that's unique to be able to show either overtly or covertly that a document or an item is not counterfeit. We also play in the solar industry. I have regular solar panels shown in that picture, but we work on a transparent solar harvesting technology or a solar window, being able to generate electricity from windows. And then obviously agriculture, which is what I'll be diving more into here in this talk. So, if we're going to talk about agriculture, we should lay some of the groundwork on what the current status is of farming and where we might be going. After all, this the theme of ScienceFest is looking forward, what's in the future. And one of the bigger things that's going to be moving us into the future to be able to feed people, by 2050 we're going to have 10 billion people on the planet, and the amount of area of land that we can farm on is going to continue to decrease. So more demand and less area to farm on. That's pointing us towards things like controlled environment agriculture. And what I mean by that is a area where you can cultivate your crops that is a enclosed area that you can condition and control the growing conditions. For example, being able to control the temperature and humidity. You can be able to control your nutrient solution, irrigation, things of that nature, to really get an optimal production out of your crops. And so when you look at things like greenhouses or vertical farms, which are under the controlled environment agriculture umbrella, you're seeing things like 10 times more yield per area for the same amount of area versus traditional field agriculture. They also use a lot less water, so it's very resource efficient. Using hydroponic systems like in this picture, you can recycle that water. You can make sure you're giving only the irrigation you need. You can minimize evaporation and things like that. So it's a really good for resource efficiency. It helps out with pests. So being in an enclosed area, you can imagine it's a physical barrier that keeps pests out. So we'll limit our needs and reliance on pesticides as we go forward, and we have more greenhouses deployed in the US and around the world. It protects your crops against inclement weather. So if you had a hailstorm or heavy winds or heavy rain or other things that might damage your plants, if you're inside of an enclosed area, you don't have to worry about that as much. And then finally, it also allows you to extend your growing season. So with a controlled environment, you can really grow year round. You can add lights, you can have your heating and cooling be able to grow during the winter as well. So overall, there's a lot of benefits to going towards controlled environment agriculture, and I think you'll see that as a trend going into the near future. So I mentioned there's a lot of things you can control in the greenhouse, but what we're focusing on today is light. And I'd argue that light is the final frontier as far as optimization goes in a greenhouse. There's a lot of things that have been dialed in on the HVAC side, nutrient side, water side, even genetics of plants, things of that nature. But with light, a lot of the technology that's gone into controlling the light environment in a greenhouse has had to do with the light quantity. So adding more light if you are in northern climates or it's in the winter and you're not getting enough light to your plants during the growing season, you can add in lights. If you're in a sunny spot like in New Mexico or other sun resource heavy areas, you might have too much light for what you're trying to grow. And so you can cut that down using deployable shade nets and things of that nature. So you can really control that light level. And when we're talking about light intensity, there's a couple common ways that we discuss it, or growers will discuss it. And one of those is the photosynthetically active radiation. And so what that means is, in short, that we call it PAR. What that means is the visible spectrum. So that same 400 to 700 nanometers that we can see is also the light that is used for photosynthesis directly. And so that's what growers really look at, is the light within those, within that range, and how much they're being able to provide to their plants. Another light quantity measure that we talk about a lot is the photoperiod. So depending on the crop that you're growing, they might require a certain amount of hours of light in a day or dark in a day to be able to fully develop and have the right plant morphology. And so growers, depending on what they're growing, will look at that as well. And so you might need to supplement light, for example, if you need more light there. And then finally, the main quantity that we want to look at as far as light quantity goes on plants is the daily light integral, and that's just how much light is it getting per area per day. That's typically how we look at it, and the plants are averaging that. So we want to, for sun-loving crops, you want to have that DLI very high. So things like tomatoes and cucumbers, those numbers are going to be higher up. Whereas like lettuce or cabbage or something like that would have a lower DLI. And if you go too high or too low, you're either going to damage the plant or not have optimal growth. So those are the types of technologies in the past that have been used as far as light. But what we're focusing on at UbiQD is really the light quality, which is really just means the color or the spectrum that we're providing the plants. And so there has been more work done now on light color, especially with the advent of inexpensive LED horticulture lighting. And that's allowed us to be able to really study how the plant is affected by different colors. And so, I've highlighted 3 different ways that color and light can affect the way the plant grows. The first is the actual structure of the plant. So for example, here on our very far left side, I've got a picture showing 3 different soybean plants that were grown under different amounts of blue light. So the total intensity or the total amount of PAR was given, was the same for each of these plants, but then the percentage of blue light was changed between each of these. And so as you go from left to right, more blue light was applied, and what you see is a difference in the structure of those plants. As you have more blue light, you're inhibiting cell expansion and you're making a shorter, stockier plant. Whereas as you decrease that blue, you're seeing that elongated plant on the left. So pretty interesting with just one color of light, how you can affect what the plant is doing as far as its structure goes. Another fun one that I love about plants is the shade avoidance response. And so the way this works is like the diagram shows, if you have some mature plants that are surrounding a new plant or a developing plant, you can imagine that those mature plants are absorbing a lot of the red light, but far red light is less absorbed by leaves. And so more of that is coming down to the immature plant. And so what that small plant is doing is it's looking at the ratio between red and far red light. And if that ratio is leaning more towards far red, it knows that most likely what's above me is shading me out and that I'm not getting enough sun. And so how it will respond is to elongate and try and get up above whatever might be shading it, or it might take a path that will be getting it out to more sun. So pretty cool response from plants to be able to grow and make sure that they survive, just looking at 2 different regions of color. Obviously photosynthesis is a major factor when it comes to color. There's been a lot of studies looking at how different colors of light affect photosynthesis, and this curve is well known. Many people call it the McCree curve based on the scientists that established it for a bunch of different plants. Others people call it the action spectrum. Basically what you should take away from it is dependent on the color of light, it's showing how efficient photosynthesis is. So on the right side here in the orange and red, those are the most efficient colors of light for photosynthesis. Obviously, we can't just dump a bunch of orange light and nothing else into a plant. There's more things that go on with other colors. You need to have all of them there, but you can tweak those a bit. And finally, with light color, one effect that can be seen is the absorption of those different colors within a leaf or in a plant. And so I really love this representation of showing how chlorophyll absorbs different colors of light. These are false colored images to show you which exposure the leaf is getting. But what you see there is the red and the blue light on the left and right there are being absorbed in that very top layer. They're very well absorbed by leaves, whereas the green is penetrating deeper. And what you can think about this is if you're absorbing a lot of the blue and the red light and the green is able to pass through more, as you have a plant that's growing taller and taller, you're having more leaves down below that are being shaded by the upper canopy. And that upper canopy is, absorbing all that blue and red light, but the green light is able to pass through. And so really the green light can dictate, how much more production you would have. So if you were able to add more green light, you could potentially be boosting photosynthesis there. So some interesting things there with light quality and color. And it really was what got us excited about it, because we have the ability to change spectrum of color, right? And so we developed a product that we call UbiGrow. Simply put, it's a layer of light that would go inside of a greenhouse. And what I mean by that is it's this retrofit luminescent film that has our quantum dots embedded into it, like you can see in the photo here on the left. And it basically sits right underneath the facade and is able to change the sun spectrum to provide better quality light to boost production in your greenhouse. And so, if you think about a greenhouse, you can really break it up into different layers where, if we look at the outside layer, we would call that maybe the facade, which could be anything from glass to a rigid plastic or even a flexible plastic like polyethylene. That's your outer covering. Underneath that is your structure layer. So these are your metal structure and architecture that's holding everything up inside the greenhouse. Usually below that comes your, what we like to call your light layer. And this is where UbiGrow fits in, as well as the other technologies I was talking about. So if you have shade curtains, you'd be putting that in this layer, supplemental lighting, which is depicted here, as well as our luminescent material would be in that lighting layer. So where you can manipulate light. Below that, you have space for air handling, so HVAC, humidity, temperature, CO2, all the things that you need as far as circulation for the plant. That would be the next layer. And then finally at the bottom, we see where the plants are. And so that encompasses everything from what kind of plant you're growing to what you're growing it in. Is it hydroponic or is it in pots, for example? How are you irrigating it? What kind of nutrients are you giving it? And so you can break these all up into different layers and optimize each one. And where we fit in is in that light layer. So, what does the product actually do? How does it work? As I mentioned, quantum dots are very efficient at changing one spectrum to another. And so we're taking advantage of that property here by absorbing light that isn't useful for photosynthesis, for example, ultraviolet light, and then other sections of light, such as blue, where we can reduce the amount of blue light being seen by the plants. And we're converting that to this orange spectrum, which, if you remember that McCree curve, these orange and red wavelengths are the most efficient for photosynthesis. So we're essentially being able to take what we can from the blue and UV side and shifting it to this more efficient color of light to improve your photosynthetic efficiency, which is our first value proposition of UbiGrow. Another aspect of it that is beneficial to plants is its diffusive characteristics. So it's been long known that if you have diffuse light provided to plants, meaning light can come from all different directions instead of direct light, which is all in one direction, you can get light to penetrate deeper into that plant canopy. And what that means, there's more light being absorbed by more leaves. It's going to stress the plant less, and you can have higher photosynthesis from that. Well, since our material is absorbing light and then re-emitting it, that emission is in all different directions. So essentially, you're getting that diffuse light of very high efficiency color with the orange glow into the plant canopy and penetrating deep. So that's another reason why we're improving photosynthesis. And then finally, the colors of light that we're shifting to also trigger responses in the plants to put more of its energy into, say, fruiting or flowering. It depends on the crop that you're growing and where you're growing it, but these colors can, promote more assimilates going to your fruit or flower, whatever you're trying to grow into the greenhouse. So I have a quick table there to show how much we're moving. Roughly speaking, we're absorbing about half of the UV light that's available, about 25% of the blue light, And then we're boosting slightly in the green and then definitely in the red section of the spectrum. So you can see that in the graph there as well. So, UbiGrow is a new technology. There aren't really any other products like it out on the market that are really focused in on just boosting crop yields from luminescence. And so, over the last few years since we've developed this technology, we've needed to go prove it out in the field. And so that requires us going out to academic partners as well as commercial growers and putting it up into the greenhouses and seeing how plants respond to the spectrum of light that we're giving them. And we also want to do this in different areas and different constructions and things like that. So we've completed over 50 different trials. We have ongoing or completed over 50 different trials, which covers 5 different US states. We have our material in 4 different foreign countries in these trials. And we typically see yield improvements ranging anywhere from 8 to 20% in overall production, which is great. We're really trying to be able to boost that bottom line by having a more efficient crop production in a greenhouse for the grower without having it be too expensive or have any operating expense like you might have with supplemental light. We also, like I mentioned, looking at different types of vegetables. So we have trials on tomatoes and cucumbers. This year we started some work on strawberries, and we're looking at doing peppers as well. And then we've looked at lettuce in the past and are going to continue to do that in our trials. So we're pretty excited about the results that we've been seeing from these trials here on Earth. But, I mentioned in my title, we want to talk about space. We want to look forward to what happens when we want to grow plants in space. And so I wanted to kind of touch base on where we are, at least from the US, but also internationally, as far as growing plants in space. As you can imagine, there's some different challenges with growing plants in space, or with no gravity or microgravity, as well as power needs, space needs, and whether or not the plants will behave the same way. And so NASA has instigated this vegetable production system that's been installed on the International Space Station. There's a picture of it there on the left. Basically, I think there's 2 chambers now, if I'm not mistaken, where they can grow different plants, typically looking at leafy greens for food. They've also done some ornamental plants as well to see how those behave, and doing experiments on plants in space. But the real goal is to design a low power system to grow fresh food for astronauts. As many of you know, astronauts' meals consist of freeze-dried, food. And, as far as from what I've been told, astronauts' sense of flavor also is muted in space. And so, what they really are asking for are fresh fruit, fresh vegetables would be great. But then they're also looking for things that can provide spice. I guess spice is one of the flavors that is still pretty potent when you're up in low Earth orbit. And so exciting thing for New Mexico is the Espanola chili pepper is been nominated as the spicy pepper that's going to be grown in space next. And so pretty proud of that coming from our neighbors, and being able to have our chili peppers going to be grown in space, and curious to see how the astronauts will like that. I mentioned there are some challenges with growing plants in space. Mainly water is one of the biggest ones. I'm sure many of you have seen different videos of how water, acts in space and how its surface tension holds it all together. Well, without gravity and without, being able to get the water to easily move to the roots and away, you run into problems with, flooding your plants, or you might not give them enough. And so right now, believe it or not, they use a syringe to inject water into what they call, I think they call it a water pillow, which is where the roots are stored. And it gives just enough water so that they're not overwatering the plants. And then they're able to, pull that water back out as they need. And so definitely some bigger challenges than what we have here on Earth as far as growing plants. And this is what we're doing today, or what NASA is doing today up on the ISS. as well as, you know, the international partners up there. But you know, if we're going to go deeper into space and potentially have humans be able to have a habitat on, say, the moon or Mars, we really have to start discussing what kind of structures we could build that would allow for fairly large sizes of production of vegetables. And so obviously there's new challenges here, engineering challenges of making sure you have a structure that can be collapsible and then deployed, hopefully slightly autonomously, you know, before maybe astronauts would get there. It needs to be lightweight. It needs to be very efficient with its resources. And so, you know, our academic partners at University of Arizona have been working with a company out of Tempe called Sadler Machine Company on a Mars lunar greenhouse prototype. And these are photographs of what those prototypes would look like. Essentially, you have a cylinder with these metal structure, you know, a circular metal structure that can collapse down about 1/5 of its deployable size. And then you're able to do hydroponic grow of plants inside of this cylindrical structure. And so you have your vine plants that kind of go up along the outside, and then more of your leafy greens that might sit down in these troughs that you see in this bottom right corner. And so, you know, what they really want to be able to do is produce enough food to make a dent in the caloric intake of astronauts. As you can imagine, the farther we go out, it's going to be harder to send supplies and meals to them. So being able to have the astronauts grow it themselves would be really important. Other things that you'd want this type of system to do would be to, you know, help convert some of the carbon dioxide breathed out by the astronauts into oxygen that they can breathe. You know, recycle waste to be able to help grow these plants and have the nutrients available for them, as well as the food that they could provide. So, you know, this project's been going on for over 10 years, and we recently partnered with them and NASA on a STTR contract to try and see if we can make this system be even more efficient using our quantum dot technology. And so, typically, when you get into these types of contracts, you will want to do something that's a feasibility experiment, show that the technology you're proposing is sound and it would actually be feasible in a deployed prototype, you know, later on down the line. And so we set up some experiments where we really wanted to show how the spectrum of light might affect the growth of lettuce in a custom-built test stand. So this is you can see on the right 3 different light treatment areas where we have artificial lights above the films that are mimicking the solar spectrum, a nice broad white light. And then below that, we have these 3 different films, 2 quantum dot films, one that emits in the red, 660 nanometers, and then our typical orange film, which is emitting at about 600 nanometers. And then we're comparing that to a control film where we really wanted to keep all other growing parameters the same, including light intensity, as best we could, where any differences in the plant growth would really be due to change in spectrum, the quality of the spectrum. And so after doing these experiments in partnership with the University of Arizona, we were able to get the results back, and they were very positive. We showed a 9% improvement in dry biomass of the lettuce under the red quantum dot film. And when I mean dry biomass, I'm talking about the actual leaves of the lettuce that have then been dried out so that we're removing all the water that might contribute to the weight. And we're really just looking at what's plant matter. We want to see, that's an indication of how well photosynthesis was operating in these plants. And so it was really nice to see almost a 10% improvement in dry mass under the red. And then we had an even further boost with the orange quantum dot film up to 13%. And so this was exciting for NASA. They really liked these results, and they awarded us a second contract, a phase 2 contract, where we're going to explore even more colors of quantum dot films, and everything from green out to far red, and maybe even combinations of different quantum dots to really see if there's a more optimum spectrum for different plants. And so we'll be using the same test stand, looking at lettuce again, but also more complex plants like tomatoes. And then we'll be taking the best performing films from that and actually moving them into a greenhouse where we'll be able to see under natural light, how the spectrum might still be performing, and make sure that what we're seeing in the small tests, that it's going to translate to the larger grow areas. And so, all this is great, but, when we do tests on Earth, in a greenhouse or even under artificial light, it's not necessarily mimicking what we might see on a space mission. And what I mean by that is we have to take into account some other factors. For example, the atmosphere on Earth is different than what you would see on Mars or even on the Moon, where you have no atmosphere, right? And so when we look at the spectrum coming to our planet, through our atmosphere, a significant amount of the light from the sun is being absorbed, which you can see in this graph on the left that's colorful. You're seeing a lot of UV absorbed, and we're also seeing a bunch of dips here, which is absorption from our atmosphere as well. As soon as you go into low Earth orbit, and you're basically away from that atmospheric effect, you see that intensity grow quite a bit. And that's what this orange curve here is what the spectrum looks like if you were on the International Space Station, for example, or similar to what you would see on the Moon if you were measuring it there, which is very close to the ideal black body that the sun is. And so, if we're on the Moon, we have to take into account that there's going to be a lot more UV and blue light, just light in general, for us to be able to convert. So we might even be able to produce more from what the results we see here on Earth. When you move to Mars, there is an atmosphere there. It's different than composition than what we have here on Earth. So there'll be some differences there that we'll need to think about, but it's also further away. And as you all well know, light dies off with distance. And so if you look at how much further Mars is from the sun than the Earth, the Earth is roughly 93 million miles away from the sun, which is commonly referred to as an astronomical unit. And Mars is about 1.5 astronomical units away from the sun. So it's 1.5 times further away, which equates to about a third less light being received at Mars. So when we really get serious about potentially deploying this technology on deep space missions, we will have to take into account what is that light we're actually going to be using in the future. It's not going to be the same as what we see here on Earth. And, it could be that we want to mimic what's on Earth to make sure the plants are operating or growing well. And then again, we might just be able to produce more because we have more light that we can, modify. And so another challenge that we also have to consider, and NASA thinks about a lot, is especially in places where there would be no atmosphere, you can't just necessarily put a greenhouse on the surface of the Moon, for example. And the reason for that is there's a lot of high energy particles out in space that our atmosphere and our magnetic poles protect us a lot from. So we're not actually typically experiencing those vents. But when you're out on the Moon, you don't have that protection. And so if you were to build your greenhouse out there, you would have radiation issues with your plants, with the structure, potentially the covering that you're using. There could be a lot of issues. And so a lot of the designs that go into a grow habitat that might be on the Moon require that chamber where you're actually growing the plants be either partially buried or completely buried, so that the regolith on the Moon is able to give you that protection. And so, as you can understand, if you're burying the thing, you don't have direct access to the sunlight anymore. So some of the ideas that are being discussed are actually collecting the light outside on the surface and then being able to pump it in using fiber optics. So being able to guide that light over long distances using these fiber optics. And so one of the things that we proposed to NASA is to be able to use our quantum dots to not only help harvest that light and guide that light through the fiber optics, but we can then also modify it. And so we did a test trial of this. It was about 1.5 years ago, I believe now, in a greenhouse in New Mexico, where we have this collector area, which you're seeing in this this left picture of these orange quantum dots embedded in a polymer. And then we have fiber optics that are coming out of that. And so they're collecting light, converting it, and then sending it through these fiber optics. And in this case, what we were wanting to see is if we provided more light to the lower canopy, would we see a yield improvement? And in this first study, we did see an improvement in tomatoes of about 7% using these, we call them luminescent solar concentrators. And so you can see pictures here in the middle also of that light coming out of the ends of the fiber optics. And then here's me in lab actually testing it on our lab bench, showing, exciting it with blue light, the amount of light that might be coming out of it. So in a true application in space, on the moon, we'd be wanting to make these much larger, or even potentially put them inside of the greenhouse after you've delivered the sunlight. But then that also gives you a lot of flexibility on where you're putting that light. So you can really manipulate where light is and avoid shading of crops from one another. So that's something that we're really excited about. So I think we're at time, and I just wanted to allow some time for questions and answers. Obviously, there's a lot more we could discuss about what's going on at UbiQD. So I wanted to point you to two resources if you guys are curious more about our company or about the brand UbiGrow. So we have our website, www.ubiqd.com, where you can see our team and what we've been working on lately, any news that has been recently posted about us. And then on UbiGrow, we've got case studies that you can go look at. It's a really nice website that can give you, more technical details of the product as well. And you can actually go out and buy it. You can shop the film and put it into, if you have a greenhouse at home, and see if you can't improve your tomato yields or cucumber yields, for example. And so with that, I just wanted to thank you all for your time. And then I think we have some questions that we can answer. I think we have about 15 minutes or so to go through those. But if you have any more, I have my email there. Feel free to reach out to me and ask any questions you might have, and I'll try and respond to those as quickly as I can. So thank you all for your time.
Great. Very exciting stuff, Dr. Bergren. And we do have a few questions.
Great.
The first one, so how soon will quantum dots go to space?
That's a great question. It's hard to say. It depends on who you talk to. I know the SpaceX folks are wanting to put people on Mars soon. I think in the next couple of years, we're wanting to start at least try and build things on the moon. If I were to guess, I think we're still quite a few years out to be able to do that. But it really depends on what we can provide to NASA and some of these private folks that are really making leaps and bounds on space travel and getting things up into space and doing it safely. I don't know if many of you guys tuned in this year, but watching that SpaceX launch with the 2 astronauts up to the space station was really, really interesting. So, optimistically, the next 5 years, 6 years, but you never know.
Great. Okay. Here's an interesting question. Is there a difference on the lifetime of the films when comparing the environment on Earth, space, and Mars?
Yeah, so I would imagine there would be. Obviously, that's a harder thing for us to test right now without being able to send them to each location. But for example, on the moon, you have more light available. And one of the degradation mechanisms that can occur with quantum dots is what's called photooxidation. So that means you have to have an oxygen species present with light to be able to degrade the dots. And when I mean degrade, that means actually not allowing them to do that luminescent property anymore. And so the way we protect against that is to actually shield the quantum dots using barrier films. You could also use other types of barrier materials like glass to help protect them more. But the more light you have, and if there was oxygen available, say coming from the plants, those are going to be our main degradation mechanisms. That being said, it's something we're working on every day, making the dots self-stable. So, the hope is one day we won't even need any barrier layers, and the dots can be directly put into different materials themselves and last a long time. And then, as I mentioned in the talk, if you don't go through the right precautions of protecting the structure from, say, high energy particles, you could have degradation mechanisms there. On the other side, if you are able to have this out in space, there's not a lot of oxygen in vacuum, right? So potentially you'd have really good stability out there. So it'll be something that we'll be excited to learn once we can get something up into space.
Absolutely. So I have a question of my own. So you saw the movie, read the book, The Martian?
Yep.
Okay. How realistic was that?
It got some things right and it got some things wrong.
Typical?
You know, yep. So I think they had some good scientific advisors. I actually know one of the guys that advised on that movie. So overall, they did a pretty good job. Being able to show how you'd have to, reclaim waste to be able to help grow your plants and things like that. One of the unrealistic things I think would be having a single person trying to develop all that without any experience. Obviously, having a trained professional that could be able to go up and grow those things and all the other operations and engineering would be really hard. But overall, I thought it was pretty good. And most of the plant biologists I hear talk about it, for a movie, it did pretty good.
Okay. All right. Very good. So here's a question. We're all wondering, what can you tell us about cannabis and quantum dots?
Yeah, so we do have people interested from the cannabis industry. It's obviously something that's popping up in the US and around the world for its medicinal properties. So we have had some of our customers asking about it and have done some trials. It's very similar to a lot of other plants. Basically, if we can improve photosynthesis, we have benefit for a lot of these plants. And that's what we've been also seeing with some of the cannabis trials that we've been seeing, or that we've been doing at commercial trials.
Okay.
So yeah, it could be an industry that could really like it. We're really focused on being able to help feed the cities of the future. We think that's really the long play and really where this technology is going to go. But obviously right now there's a lot of money in the cannabis industry, which is good regardless of how you think of it, because it's plowing the way for a lot of technology and innovation in controlled environments. So as that becomes more ubiquitous, they're going to need to find cheaper ways to get better yields, and our product could be one of those.
But you're not going to relocate to Colorado.
Not anytime soon that I hear. No,
Okay.
I am from Colorado, but I love it here,
yes.
and I think our team does too. Los Alamos is a great place.
Excellent. That's what we like to hear. Okay. So we're wondering, what made you want to study quantum dots and research them, and what recommendations do you have for someone that would want to go into this field?
Yeah, no, it's a great question. My route was a little wandering, like most people do. I originally went to school wanting to be an engineer, and found out that I had this a deep desire and love for physics with my courses there, and it really is having good professors that open up the doors for you, and then having the ability to go into the lab. I always wanted to be a scientist, and so my mantra with education is keep as many doors open as you possibly can, because you never know which ones you want to go walk through. And so if you say yes to as many of those as you can, while also trying to focus, opportunities will come your way. So I'd say, don't take for granted your courses that you're taking in middle school and high school. They come in handy when you get into being a scientist, if you're even in a fancy lab. And really, go after what you're passionate about. I was passionate about solar energy, renewable energy, and nanomaterials at the time when I was in school were and still are, one of our biggest technology advances for that field. And so I was just fascinated by it. I really enjoyed the discovery of science, and specifically in nanotechnology. Being able to be the first person to discover something is really amazing. So it takes a lot of hard work. It takes some stressful times, but as long as you're in there working with your team and working hard and going after what you're passionate about, I think you'll find any of these science areas are amazing, and you'd really enjoy it.
Okay. How does the shape of the visible light spectrum on Mars compared to that on Earth?
Yeah, so it's a good question. It's going to be still having that black body type of overall spectral curve to it. What you're going to find that's different is the intensity, like I mentioned, is going to be about a third less than what we're seeing on Earth. But then because that atmosphere is different than ours, and you know, unfortunately, I don't have in front of me what the composition is, or have a figure that I could show you, but you can imagine those dips are absorption from aerosols in our atmosphere. And if there's a different composition there, you're going to have different absorption patterns there, and wider gaps potentially of where you're absorbing. So overall, you know, to most people's eyes, I think it'll look about similar, but with less intensity is what you're going to see.
Okay. All right. So I want to just share that I'm lucky enough to have a piece of the film. It's the bookmark, which you can get, I believe, on your website. You can actually get this at locally at the gift shop inside the Bradbury. Unfortunately, both of those are closed, but if you go to the Bradbury Association website, you can order these through Gadget's online store now. And
That's right.
you're the biggest nerd in any room when you have one of these. So
they're great gifts to give people. Having so those are actually part. They're cut from the scraps of our UbiGrow film. So we want to try and make sure we're utilizing our material best and reducing waste. And so this is kind of a fun thing that you can have and put into your books and shine a light on it and see it glow, or put it out in the sun. So yeah, thanks for saying that, Ren.
Stuffers.
That's right. That's right.
Super fun. So let's see. Do you use different kinds of quantum dots, or are they the same?
So yeah, our company mainly stays with copper indium disulfide and diselenide and alloys of those materials to get into the technical part of it. Our team has a lot of experience with a variety of different compositions, going all the way from cadmium selenide to, you know, I worked with lead sulfide, silicon quantum dots I've worked on in the past. So definitely have the expertise to do so. But right now we focus in on this system for the reasons that I mentioned earlier. You know, the toxicity concerns aren't there, ease of manufacturability, and there's some other optical properties that are really interesting for it with light guiding that help us out on our application. So we mainly stay there, but we always like to keep tabs on what other people are doing as well.
Sure. Can this be used on algae?
Yeah, actually, that's something we have talked to different scientists in town and off the hill as well about. I think so. You know, anything that where we might be able to improve the photosynthetic efficiency of a plant should work well. We haven't done any testing on it yet, so I will put the caveat there. But would be interested in doing that if people have a project that they'd like to work on.
Great. One last question from the audience, and then I have one. Can quantum dots filter harmful radiation?
Yeah, so harmful radiation is a bit general. I can tell you which harmful radiation we can filter in the sense that we absorb UV light, and UV light obviously can be harmful. And so we absorb UV light very, very strongly and can convert that to useful with light. As far as maybe if they're talking about, you know, cosmic rays and things of that nature, I haven't personally looked into the absorption cross-section of those. But I do believe there were some researchers that were using quantum dots as scintillators, so doing detection of cosmic rays. So I assume it's a non-zero absorption cross-section there. But I'd say for now, really it's the UV light is what we're able to filter out that would be harmful radiation.
Okay. And my last question, what's next for UbiQD?
What's next for UbiQD? So right now we're really focusing in on how we can develop this product further. So I mentioned different colors into our quantum dot films. You know, what we envision is being able to have different light recipes depending on what you're growing or where you're growing. So we're really, with the NASA project, specifically looking at, you know, what these colors of light can do for different types of plants so that we might be able to sell to your tomato grower up in the Great Lakes area a certain recipe versus maybe your lettuce grower in Southern California. So on UbiGrow, that's really what we're looking forward to. You know, we're also looking to expand that into other types of products. So putting it into the glazing, for example, having it be a part of the glass in a greenhouse or on the polyethylene cover. So when you're actually changing out your facade, you can add in the quantum dot capability. And then the other big ones that we're really excited about right now are the other industries we're working in. So, you know, our solar window products are being developed. We're going to be installing those into buildings this year and testing out those performances there. And we've been doing a lot of work on security inks, which unfortunately I can't talk as much about for obvious reasons, but you know, exciting stuff there. And then being able to continue to use this technology for you know, more applications down the road, and bringing more
Very
people to Los
exciting.
Alamos.
What's that?
And bringing more people to Los Alamos.
Excellent.
Hiring
That's
more
what I
people
like
and
to hear.
growing.
Very exciting stuff. So I just want to say thank you to you, Dr. Bergren. This is really exciting work you all are doing, and we're thrilled to have you here in Los Alamos. For those of you that want to share this talk, the recording will be available later. It will be under the event schedule on the app. And if you have further questions, I know there was one question we couldn't get to. You can pose questions to Dr. Bergren on the event app, or you can email him directly. And on behalf of ScienceFest, thank you again for your sponsorship and for this wonderful, interesting talk.
Yeah, thanks for the opportunity. And I'm looking forward to this weekend. It's going to be a fun closeout of this week.
We all hope to see everyone at the Discovery Day that you all are going to be at. So
yeah, that's right. Come check us out on Saturday.
Virtually. Great. We'll see you then. Thanks very much. Have a great evening.
You as
Thank
well.
you.
Thanks, everyone.